Hello and welcome to today's video on standard form. As you can see, I've written a really long number out here. It's got a 3, a 7 and then some zeros, and it's not immediately obvious how many there are. And if we wanted to work out exactly how big this number was, we'd have to start by counting the zeros. You may well have seen normally in large numbers people put commas every three digits, working from the right to left. So let's start by doing that. Okay, so we can now see much easier. We've got 15 zeros. So we've got a 3, a 7, and then 15 zeros. And so how big exactly is this number? Well, the first 3 zeros are 1,000. Then you get a million, then a billion, then a trillion, and then a quadrillion. So this number is actually 37 quadrillion. If I can spell, I apologise. And now that's a massive number. It's not a particularly useful number, but it's massive. And you see how hard it is to tell exactly how massive it is. Then if we compare it to something like 37 trillion, as far as we're concerned, they're probably just both really big numbers. Except sometimes we need to know precisely how big, or certainly how much bigger it is relative to something else. Because obviously you think of 37 trillion, it's a big number. 37 quadrillion, it's a big number. But obviously how much bigger 37 quadrillion actually is not immediately obvious. It's 1,000 times bigger, but what does that actually mean? Is there some way of writing these massive numbers in a way that makes them a lot more comparable? And the answer is yes. So if I write out 37 quadrillion again, I don't know why I rubbed it off, but hey ho. 3. So there, we've got 37 quadrillion. And what you may notice is that this is just a 37 with 15 zeros after it. And I'm going to start with a slightly different question now. What is 37 times 10? Make my 7 a bit clearer. That's even worse. There we go. I assume you can all work that out. That is 370. And all we've got is our 37 with an extra 0. So 37 times 10 equals 370. 37 times 100, and as I'm sure you can all work out, is 3,700. But 100 is 10 squared, so we get 37 times 10 squared equals 3,700. And if we continue this, obviously we've got 15 zeros and 37 quadrillion, so we could write 37 quadrillion as 37 times 10, and then as we see, if we multiply by 10 to the 1, we get 1 0, 10 to the 2, we get 2 zeros. So if we want 15 zeros, we're going to multiply by 10 to the 15. And this is the basis of standard form. Standard form is taking a number, giving it its relative sort of value, which is the 37 part, and then displaying really obviously its magnitude, quite how large it is, and that's the 10 to the power of whatever. That's your standard form part. Except we're not quite done. Because one of the rules of standard form, if you have some number a times 10 to the b in standard form, a has to be, oh, I've done that wrong, between 1 and 10. So A has to be, well, a single digit or a single digit followed by a decimal. So in this case, 37 is not between 1 and 10. So we'd have to divide 37 by 10 to get 3.7. But because we've divided by 10, we can't change the number, so we still have to multiply by another 10. So 10 to the 15 times 10, using our power laws, is just 10 to the 16. So 3.7 times 10 to the 16 equals 37 quadrillion in standard form. Oh, I cannot write today, I apologise. So standard form is just taking your number and basically taking all of the powers of 10 out to one side until you're left with a number between 1 and 10. And it can be 1, so if we had something just like, we'll take 1,000,000 here, we would write that in standard form as 1 times 10, and then as you can, oh, that's 10. As you can see, we've got 6 zeros, so that's just going to be to the 6. What you can't do is have it as 10 times 10 to the 5. That is not standard form. Okay, so let's give you a couple of examples. Let's go with 42 billion and why not 6,410,000. Right, both these in standard form. Feel free to pause if you need a bit more time. And okay, so 42 billion, first of all, equals 42 times 10 to the 9, because we've got 9 zeros, but then we need to get this between 1 and 10. If we divide by 10, we get 4.2, but we have to multiply by that 10, so we just raise the power by 1. So 42 billion is 4.2 times 10 to the 10. 6,410,000 is 641 times 10 to the 4. Again, we need to get it down between 1 and 10. Divide by 10, we get 64.1 times 10 to the 5. Again, we have to increase the power by 1, multiply by another 10. That's still not between 1 and 10. So we can divide by another 10 and we get 6.41 times 10 to the 6. And this just allows us to compare numbers of different sizes. This is particularly useful in things like science, where you do get some massive values, like the speed of light is about 3 times 10 to the 8 meters a second. Those sorts of large numbers, if you can express them in standard form, they're a lot easier to work with, as much as anything, because you can just remember that there's a 10 to the power. Standard form also works the other way. So if we had some number like 0.459, that's not in standard form because it's not between 1 and 10. So what we do is we can multiply it by 10. We get 4.59. So it's standard form, so we need the times 10 to a power. But what is the power? Well, 0.459 equals 0.459 times 10 to the 0. 10 to the 0 is 1, timesing by 1, no change. But as we've multiplied this bit by 10, we need to divide that bit by 10 to keep it balanced. If we divide that by 10, we just decrease the power by 1, get 10 to the minus 1. Equally, you can think of it 0.459 multiplied by 10, and then times by 1 over 10, which, as we also know, is 10 to the minus 1. So, and this works for any decimal. We could have 0.00000073. So we're going to have to multiply that by 6, or 10 to the 6, sorry, not by 6. It's 7.3 times 10 to the minus 6. So, basic rule is if you have some number, let's call it ABC, with some zeros after it, you start by counting the zeros. So you then get ABC times 10. Let's say there were n zeros, 10 to the n, and then you divide your number ABC, so you get AB point C times 10 to the n plus 1, and A point BC times 10 to the n plus 2, and that works whatever. So it could be, as we saw, 6,410,000. It could be 5,439,600 million, etc. You see, this is why standard form is useful, because if you get large numbers, keeping track of exactly what they're called is quite hard. But if you say something like 5.649 times 10 to the 8, it's a lot easier to remember, it's a lot easier to say than something like, 54,730,000,000. So if you have a really large number, count the zeros, remove the zeros and times 10 to the power of the number of zeros, and then do any more divisions and increasing the powers until it falls between 1 and 10. If you have a really small number, so something that's a decimal, such as your 0.00000073, again, count the zeros, multiply by 10 to the negative that power, and you'll be done. So here there are 6 zeros, so it's 7.3. That's between 1 and 10, that's fine. You just move the decimal point to after the first, but because there were 6 zeros, we then times by 10 to the minus 6. So again, practice. What is 0.000000000462 in standard form, and 0.005391 in standard form? Do pause the video if you want more time. But okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8 zeros in the first one. That is a rubbish 4, but you get the point. So we know it's going to be 4.62, because that's between 1 and 10. We move the decimal point to after the first non-zero. By the way, if we had something like 4062, that zero is now part of the number, so it would be 4.062. It's only the first non-zero. You only ignore zeros before the first non-zero digit, or indeed after. So if we had 3,078 or 3,078,000,000, because this zero it has numbers after it, we call it it's significant. I'll do a video on significant figures in a couple of weeks where I'll explain this more properly. But just for now, remember, it's just any zeros that start basically in the unit. So either the furthest right and work your way left, or the furthest left and work your way down through the decimal points. So this one, it's 4.62 times, because there were 8 zeros, it's 10 to the minus 8. And then this one, we've only got 3 zeros. It's going to be 5.3971 times 10 to the minus 3. That's all for today. In fact, my next video will be on significant figures, as it ties in quite nicely with this. So I'll explain more about what counts as a significant figure, what doesn't, and how we do significant figures. Until then, keep doing maths.